session. Yeah, I think recording has been started. So I'll just say that again. So my name is Hemant Urdhwareshe and I'm a mechanical engineer. And I passed out from VNIT. That time it was VRCE Nagpur. And I'm a mechanical engineer. Then I joined Kirloskar Cummins then. Now it is called Cummins India Limited. I worked there for 28 years. I was head of quality and then head of engineering and reliability there. Then I started this Institute of Quality and Reliability in 2005 and still working with many corporates and individuals. The corporates that we work are Ashok Leyland, Tata Motors, Mahindra and Mahindra, many automobile companies and other companies as well. And then individuals, we work for training the individuals who are interested in getting certified from American Society for Quality as either Six Sigma Black Belts or reliability engineer and these kind of things. So I'll be conducting totally two sessions, and today what we are going to do is we are going to discuss the basics of and tomorrow at in the first session we'll continue that part, but we will go to the fractional factorials tomorrow. And tomorrow's second session will be conducted by our other faculty member, Mr. Yashwant Mahakal, that is on the response surface methods. So this is actually a total set of three sessions wherein we will try to explain the basics of experimental designs, how to structure the designs, how to analyze the designs. We will try to introduce Minitab software. I believe many of you might have downloaded and installed the Minitab software, which was my instruction for the session. So I will now share my screen, friends. I hope you are able to see my screen. Are you able to see my screen? Can anybody confirm?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. One more thing I would like to share that the topics that we are going to cover here and also in this faculty development program that has been planned very well by VIT and the team, Medha madam and all the team. So I realized that many of our YouTube videos, which I created in the last 4 5 years, they address at least 60 70% of the topics that we cover here. So I have provided a list of 100 videos along with the direct links to the YouTube channel, wherein you can directly go to that particular topic and see more details. The DOE session that we are covering, there are total, I think, 9 or 10 or maybe 12 videos on this topic. There are about 10 on the inferential statistics, which probably was covered yesterday, I think. And then you got the thing that we are correlation regression gets covered into the videos. The topic that is not covered is the multivariate analysis, which will be covered by Ekagra Chennai. With that, let me start this session. Any comments before this before the start of this session? I think I can start, right?
So YouTube channel name, please. So YouTube channel name.
That the list has been completely sent to Vrunda and Medha madam, but I'll just show you that channel also, not a problem.
Yes, sir. Yes.
See, it is basically, if you look at this, our material, there is a direct link to that also. And this PDF has been given to you. Have you received this PDF copy? Have you received the PDF copy, friends?
Yes, sir.
Okay, so on the very first slide, you will see YouTube channel link, wherein you can just click on this or copy and paste the link, and you go to the channel. I'm just doing that just because you asked a question. So I'm just pasting it, and you can see that you go to the channel directly. This is and you go to videos. You will see all the videos. If you want to go by some topics, then there are playlists also created. There are 10 15 playlists on different topics like DOE or sampling plans or whatever it is. So you can use this later on. Right now we'll focus on the lecture, today's lecture. This is a live lecture, so we'll continue with that.
So one small doubt.
Yes,
We did
please.
receive Minitab link. I registered for the same, but there was no download option available. Like I'm able to
There
use it
is,
in Chrome.
if you click on this minitab.com,
There was a link which was shared with us in the morning.
no, doesn't matter. You
I registered.
minitab.com, it just, even if you just go do a Google search on Minitab,
Okay.
you will reach this website, and then we are here, and this is, we are Minitab products, Minitab statistical software, and you can just click here, and then you can, this is the software, and there should be a download link somewhere here. Yeah, free trial. Can you see that on the screen?
Yes, yes.
So just click on the free trial, and then it will allow you to download. Okay.
Okay. Thank you, sir.
Yeah.
Excuse me, sir,
So
may
I
I?
will go. Yes, please.
Sir, I am having design expert, so it will do or I have to go for a Minitab?
Well, I also have design expert, but this session, because Minitab is more popular, we'll be showing it on Minitab. But you can use almost the similar commands on design expert.
Thanks a lot, sir.
Design expert does all the procedures that we are following. But the only thing is that my instructions today will not be in design expert.
Okay, sir, no
We
issues.
have a separate material for design expert, but I haven't planned for this session.
Okay, sir. Okay, sir. Thank you.
So very good evening, sir. A small question, sir. Can I, sir?
Yeah,
So we are from commerce and management faculties here.
yeah.
So if you have start me with the basic, will be so helpful, sir,
We are
to
starting with
understand.
basics, so let us focus on this, and you can hold on to your questions until we go a little further,
Sure,
right?
sir. Thanks, sir.
Otherwise, we will remain here only. That's the
Yes, sir.
reason.
Yes. Thank you,
So
sir. Thank you so
sorry
much,
to
sir.
disturb again.
Yeah.
I tried the path which you showed me about the free trial. It again asks me to fill in my
Sir,
data.
can this be
Yeah, it will ask
addressed
you for your
offline?
email ID and other thing. You'll have to provide that.
Okay, and then I don't know, I'm not able to get again the download link.
I think you should have done that before, because today in the session, if we lose time on downloading Minitab, you observe,
Yes.
and there are links to videos also, so you can do it later if you feel like.
Okay,
Yes.
fine. Thank you,
Don't
sir.
worry about that. That's not a big part of this. Minitab is easy. Just focus on the session now. So agenda is introduction to experimental designs. We will have a example of DOE virtual catapult experiment, which we will analyze on Microsoft Excel. So I don't want to start with Minitab. I want to focus on the basics. Calculating the effects of factors and interactions, how to do that. Plotting of the main effects and interactions. Application example of a full factorial design on Minitab. Here we will probably go through the Minitab part. And those who do not have Minitab, just watch, focus on the session, and later on you can try it. Introduction to fractional factorial designs will be tomorrow. I have combined the agenda and the material also. So from this part onwards, it will be tomorrow. Confounding and resolution code of the fractional factorial designs. Example of a fractional factorial design. Again, we will do on Minitab. Actually, I would like to do this on Excel, Microsoft Excel, but I'm not sure whether we will have time for that. If you insist on Excel, I will show completely on Excel, and Minitab, you can watch the videos. So I will ask that question at that point of time. And then how to select the designs for your particular objective. What is the historical background of experimental designs? The DOE approach was developed by Sir Ronald Fisher in 1920s, and I'm sure you might have heard about this gentleman. And the inferential statistics, which was covered probably yesterday, if I am right. So that would cover Fisher's many of the tools and techniques. Initially, this DOE was used to improve the yield in agriculture. And Fisher also created all the theory and tables for analyzing statistically designed experiments. So there is a methodology, statistical methodology that completely supports the analysis of the designs. Later in the 1970s, a gentleman called Dr. Genichi Taguchi added a new dimension to design of experiments. And initially, when Fisher did it, it was for optimizing the mean values of the response. But Taguchi realized that not only the mean value, but variation also is important. So Taguchi added a new dimension to the experimental designs to minimize variation. And if you have this combined objective of optimizing the mean and minimizing the variation, the strategy is called robust design. We are not going to cover the robust design strategy. There is a video that introduces you to robust design in the list of videos that I have shared. Development in computers and softwares have made design and analysis of experiment much easier. So this is the first photo is of Ronald Fisher and the second one is of Dr. Taguchi. Incidentally, Dr. Taguchi is an alumnus of Indian Statistical Institute, and he used to come to ISI every year probably to deliver free lectures. He's no more. He passed away, I think, about 4 or 5 years ago. His son is there, Shin Taguchi, who still conducts some of the lectures. So conventional approach to experimentation is people depend on what is known as OFAT, and full form of OFAT is what? It is one factor at a time. So do not change too many factors at a time because you will not be able to evaluate the effects. That's the philosophy that the old school of thought. Even when I worked in Cummins, most of my seniors didn't know about experimental designs. It is only 1995, 96 when I got introduced to the American Society for Quality Body of Knowledge for Certified Quality Engineers. Then we went through this lectures on all the statistical tools and techniques, including this experimental designs. Then we tried many DOE options in Cummins also to optimize some processes. So this OFAT is basically one factor at a time, and that has got a limitation. What is the limitation or disadvantage? We will not know interaction of various factors with each other. In most of the experiments or many experiments, factors work together, they are not fully independent. So, like when you take a tablet, people say there is a side effect. So, if you got a fever, you will take a tablet for fever, and then you will say there is a side effect. I am getting some other side effect and feeling, let us say, weakness is there, or if there is a stomach upset tablet that will give you some other effect. So, there are combined effects of multiple factors. So, factors are often not independent, and that is the main disadvantage of using what is known as OFAT. Interaction means the effect of a factor depends on the setting of the other factor. And we will know about this in the even in probably in the first experiment that we are going to try online. And very shortly we'll start the experiment. This is not a theory session. We will actually do an experiment and learn about it. We can miss the optimum setting of the factors to get the best results. So let us say, what is the consequence of OFAT? First, let us say you want to optimize the speed and feed for to get the best surface finish in a cutting tool for a cutting tool, and you are machining some part. So what you will do is you will first find speed for the best surface finish, and then at that speed find the best setting of the feed. So what is going to happen is, let us say you got factor A and you will have the setting of this speed. So you decide that this speed is the best for me. And at this speed now I will try the feed and then I will get this best. So the black point, the black circle shows what you are going to get out of this OFAT. But if you actually do a statistically design experiment, it is possible that the optimum setting is not here, but it is actually here because the speed and feed may have interaction between them. And as you know, there may be built-up age on the tool, and there are technical reasons for this. Technical reasons will depend on each type of experiment that you are trying to do. But this is the main disadvantage of the OFAT. So statistically design experiments, you have less testing and more learning. From the same amount of testing, you learn much more. Interactions can be evaluated. We can find optimum settings to get the best of the process or design. Steps in DOE, I'll go quickly on this. Define what you want to do. What is the problem? What is your objective? Establish the objective, that is what you want to optimize. In, let us say, if it is a cutting tool process, you want to get the best surface finish, maximum tool life. if you are trying to develop an item design, you want to maximize the strength, let us say fatigue strength or some kind of a thing. So those that becomes the objective of your experiment. Select the key process output variable or the response. KPOV stands for key process output variable. Y or response is the that is the response from the experiment. Select key process input variables or x's. So you got y as the response and you got x as the factors. You can use a process map or you can use a cause and effect diagram, those kind of tools. So you map the process and find out which are the input factors and which are the output responses. Choose the factor levels. So what are the actual settings that you would like to try in the experiment? This requires your technical judgment, technical knowledge, technical judgment. There are few other considerations about which I'll talk later. Select the experiment design and number of replications. The number of replications is number of times you are actually performing the whole design. That also we'll talk in few moments. Collect the data, actually run the experiment, conduct the experiment, collect the data. Dr. Ranade was a little skeptical about the data, but here you are yourself doing it. So that data collection becomes important. The important part of data collection is your measurement system should be really capable and adequate for the purpose of discrimination between high, low, or whatever. Analyze the design, the technique that we are going to learn. Interpret the results, again, the technique that we are going to learn, and evaluate the benefit that you got. So these are the general steps in the experimental designs. Now we will do an experiment actually, and we'll discuss few more things while we design this experiment, conduct this experiment, analyze the data. And that is, we call it catapult experiment, but a catapult, we are going to use a virtual model. Fortunately, there is a company in the world who has made a nice virtual catapult which we can use. We will play a simple game to understand experimental designs. You open this website, you can click on this link and go to otherwise you can type in Sigma Zone and go to the catapult. I will show you the website and you will see this. I'll just open the website actually. Yes, if I click here, and even in your case, you can directly go to this. Is everybody getting this website?
So can you share in the chat box, sir? Enable to, sir.
Oh, you don't have the material, is it?
Yes, sir.
But just type in Sigma Zone, SIGMA zone. I'll put it in the chat box, not a problem. But okay, let me put it in the chat box. Okay, I put the link in the chat box. You can click on that. You will reach this website. I'll just wait for a minute for you to confirm that you got it. Is everybody able to see this catapult? I'm assuming that you are able to see.
Yes, sir.
Yes, yes, it is
Yeah.
visible.
Yeah. So what happens is this catapult has got total 5 factors and catapult settings. If you'll see here, I'll just use a pen here. Just give me a minute. Just a minute. I'm just starting a magic pen, which I can use anytime. Okay. So what you are seeing here is here. So here on the left side, here on the left side, you can see the 5 settings, 5 parameters. The release angle, the firing angle, cup elevation, pin elevation, and bungee position. So we will only use we will use 2 out of these factors for a simple experiment. Now, if you want to just try something, what happens in this catapult? Let me show you. Let us say I change the release angle. So if you change the release angle, you just use your mouse and change the release angle. Let us say I use 180 degrees release angle and I don't change any of the other settings and it throws a ball. and you can see at what distance it has thrown. So this is looking like 447 or whatever it is. I can say fire again, it goes back. And now you can change the stop position firing angle. So this firing angle you can change. So that becomes the stop position. Let us say I use 120. Now the flight will change. As you know, a catapult flight is a is a parabolic flight, and this changes now. The distance changes. So you can change various parameters. You can also pull this up and down to change the throw. You can also change this pin elevation. You can also change the bungy position as they call it. So every parameter. So what we are going to use is we are going to use two of these factors, two of these parameters. And the parameters I don't want to because usually we debate with the participant, but because of the time constraints, I'm going to suggest two of these parameters, that is release angle and firing angle. We will perform an experiment with these two factors, and we'll keep the settings of the remaining factors. Cup elevation will keep at the highest. Right now it is you can vary between 200, 300. We'll keep it at 300. Pin elevation will keep at the highest 200, and bungee position also will keep it at 200 because you can. So all the three factors we are keeping at the maximum levels. And now I go back to the material, and now let us see how we can use this. Okay, so this is the catapult that you have. I have so I said select two factors, release angle and firing angle for the experiment. The settings that I suggest. Okay, we will make a table in Excel for the factors and level as shown below. So I'll just copy this, and I request all the participants to open a blank Excel file, Microsoft Excel file. A blank Microsoft Excel file, friends. So the levels, so the table that we are making is actually this one, but I'll say I will actually make it a release angle, and I will make it a little bigger so that you can see it properly. And B firing angle. So these are the two factors that we are going to play around. And I suggest that the low level of this release angle, so I make this low and high. So most of the experiments are performed at two levels only. The reason is there about simplicity. I'm not going into the details of that. But if you go to three levels, four levels, it complicates the situation. The number of runs n, the number of runs n in an experiment can be calculated as level to the power of factors. Now here you got two factors and you got two levels. Each factor has got two levels. So n is equal to 2 raised to 2. That is equal to obviously 4 possible runs, or these 4 are called treatment combinations. I will just show you now. And I will also explain why these levels are suggested and what is the consequence of different levels. At the moment, I am just typing in 145 is the low, 145 is the low value and 160 is the high value of the release angle, and firing angle 110 and 130. If you feel that I'm going fast, the sessions are recorded, so you can do it later also. So this is the table that we have created, friends. Now, if you want to find out the number of combinations that you can have in this, I'll go to the next slide and explain this. There are 4 possible treatments in this design as shown in the design matrix. So this is the design matrix. So you have release angle and firing angle. So you set first the release angle low, low and high, high, and then firing angle low, high, low, high. So each combination is called a treatment. So row number one, treatment is 145 degrees release angle and 110 firing angle. And these are called uncoded levels, actual levels. It is often convenient, usually convenient to assign coded values as -1 for the low level and +1 for the high level. The design matrix with coded values will be like this then. So you have -1, -1, +1, +1, -1, +1, -1, +1. So this is the design matrix in coded values. I will I will explain this further when we calculate the effects. The reason for this is if you want to add an interaction column here, it is just a multiplication of the algebraic multiplication of this -1, -1. So the interaction AB will be -1 into -1. First row will be +1. Then it will be -1 into +1, -1, etc. So I will explain that again. So this is the right side is the design matrix in coded levels. The left side is the uncoded levels. And then there are, yes, please. You kindly mute yourself. So we go further. As we are interested in evaluating interactions, a column for interaction can be added to the design matrix with coded values. Coded levels of interaction column can be determined by algebraic multiplication of the coded factor levels. And here they are shown, you can see them here. You can see that AB interaction, the coded value -1 into -1 is -1 plus 1 -1 -1. I think somebody is speaking. Can I request you to mute yourself, please? Unless you got a question, which I will encourage at some point in time. So this we have done. Now we will, there are 4 treatments in this. So I'll go further. This is a single replicate. So this is known as single replicate of the design with 2 factors, each having 2 levels. Because each combination you are only trying once. But for certain reasons, if you want to increase the sample size, because if the effects are small, then you need larger sample sizes and you may need to replicate this design. So you will perform this once again. All the 4 treatments you will do 2 times. In that case, the number of runs with 2 replicates will be 2 times 4, that is 8. If you got 3 replicates, it will be 4 into 3, that is 12, etc. So that is sometimes required in case you want to get the finer value of the effects or some statistical significance for reasons, sample size you want to increase. Factorial designs are denoted as level to the power factors or L to the power F, which I have explained already. Thus, the design of this design is 2 raised to 2 and has got 4 treatments. Number of treatments is equal to L to the power F, which is also the number of runs in a single replicate, or number of trials, you can also say. Now I come to the nuisance factors. This is important. There are a number of experiments where there are uncontrolled factors. For example, in this case, what we are doing, if I go to this catapult experiment, we are going to control the release angle and firing angle. But we are not changing the other thing. But if imagine that you are actually doing this physically, and this is a wooden catapult, in that case, there will be some air currents which can affect your results, or there will be external factors such as clearances between the hinges or incorrect settings of the catapult, the tension change of the, so there is a tension that is created by this elastic band. So this elastic band might age during the experiment and change its tension because of humidity, temperature. So there are uncontrolled factors in every experiment, and you want to make sure that that affects to a minimum level your results. So there are two strategies which are usually followed. What are the 2 strategies? There are a number of experiments where uncontrolled nuisance factors can affect your inferences. Environmental on 2 different days can be different operators, equipment. there are different approaches to separate its effect from drawing inferences or minimize. The first one is randomization. That means you perform the experiment in a random order, so that any change of any wind or any temperature changes or any change that happened during the experiment, the effect of that is not associated with any particular setting. So it gets distributed evenly all over the runs. And then there is blocking. The nuisance factors are sometimes called lurking factors also. So I'll explain a little bit more about these two. Randomization means randomly without any specific order, sequencing the trial runs so that variation due to nuisance factor is distributed randomly. This will be part of unexplained variations seen in the individuals. And blocking. Blocking means considering these nuisance factors as one of the design factors, although we are not interested in the effect of these factors. Blocking means considering these nuisance factors as one of the design factors, although we are not interested in its effects. This is necessary if we cannot hold it constant or randomize. So blocking factor means these are discrete factors. Let us say we are not interested in the operators or same process is followed on two machines, but we are not interested in the machines, but we want to make sure that the machines do not contribute to the variations. So in that case, what you do is you block on machines or block on operators. Examples are shift. You are performing experiment in two different shifts because of the time constraint you have to do in both the shifts or three shifts. So you cannot control that. That's beyond your control. But shift is not of your interest. So you block on shifts or day one, day two, or material batch. So you are drawing material from different batches, heats, those kind of things. These go into blocking. So randomization is done for unknown uncontrolled factors, while as blocking is done for known discrete factors. But you are not primarily interested in the effects of blocking factors. So I proceed with that. Now we will create the random order of the experiment that we have decided. So I go to this Excel sheet now, and I create those four treatments. So let us say I create the four treatments. I have listed here. So the treatment is first. Let us say I decide the firing angle low, and that means 110, 110, and 130, 130. And then I decide release angle low first 145, then 160, and then again 145, 160. Now you can observe these are coded units, and if I do that in uncoded units, obviously I will have to do like this. So I'll just show you the uncoded. So this will be -1, -1, 1, 1. And this will be -1, 1, -1, 1. And if I create the interaction column AB interaction, then it will be multiplication of the two, -1 star -1. And you just copy this formula and you get a design matrix in coded units. And this is design matrix in uncoded units. But now I have to add a response column here. So I'll say response is distance. I'll say Y. Sorry. Y distance. And now we will actually run this experiment. Let us say we do this in random order. And the random order, you make 1, 2, 3, 4 numbers on a paper, and you start taking that sheet one by one. Let us say this happens to be the first one. I'm assuming that this is a random order. 2, 3, and 4. Yeah, why the record? Okay, somebody stopped it. Okay. So what is the sequence? The sequence we have to follow this. So the first run is actually 145, 130. Although this is the first. So this is called standard order. I will just add a column here. I will say standard order. The way I have listed is 1, 2, 3, 4. It's standard order. And the random order is actually the run order. You will see these columns in Minitab also. But we will run the experiment in run order. So first one is 145, 130. So firing angle is 130. So firing angle 130. And I think it was 145, 145. So 145 I use. And now I have to record the distance. That is my experiment. So I threw this ball and record the distance, which is 171 approximately. So I enter 171 here. This is my first run. Now the second run is 145, 110. So 110, I have to change this setting. And I think it was 145. Yes. So I pull back 145 and again throw this. Now the distance will obviously change. It's going to be more. So 328 is the distance. So I record it. The second, so 328 is the distance. And now the third run is, the third run is 161, 130. So 130, 160. So 130 is the firing angle. And 160 is the pullback angle or release angle. Yes. So this distance is likely to be even more or whatever it is. 352 is the distance that I record. So this is 352. And the last run is 160, 110. So I just change this 1 to 110. And this is 110 and 160 is the pullback angle or release angle. So this is giving me 439. So I record 439. So I have conducted this experiment and this is the first replicate that I have. I don't know. Are you able to hear me? Yeah, there was some problem in the internet. Hope you are able to hear me.
Yes, sir.
Okay.
Yes, sir.
So what?
Yes.
Yes, please. Okay. So we have done replicate one. First replicate. We will not do second replicate. In the interest of time, we will just analyze this data and see what happens to this data now, analysis of this data. I can also again copy this column here in the coded because it's in the same sequence. So I can add the coded values, right? Yeah. So now I have to calculate the effects of each of these factors and also the interaction. Now the effect of a factor is is defined as, I'll just show you. So effect is equal to average at high level minus average at low level. I mean response low level. So this becomes the effect of a factor. Now, if you want to find out the effect of, let us say, I'll make now a table. I will again, I'll make a table of this one here below. Maybe here below. Interaction. So, and I will say average at high level, and I will say average at low level. It's very easy to calculate, but pay attention so that you understand what is the simple logic. So let us say I now make a table like this. And now in the last row, I say effect of that factor or interaction. So this table will help me to calculate all the three effects. Now, as you can see that effect of a factor is defined as average response at high level minus average response at low level. And the first factor is release angle, which is this one. So I just mark the low values here. These are the in blue color, or high values in the red color. Let us say 160, 160 are high values, and the black ones are low. So the response at high level is the response average of 439, and I press the control button on Excel, and 352, average of 439, 352. Below that you will see 395.5. So this is 395.5. And average at low level, I take the average of 328 and 171. So I press control button here. I can also, of course, use the formula. So this is 249.5, 249.5. And now effect is just a difference between this. So 395.5 minus 249 gives me the effect as 146. What is this 146? This is the effect of change in release angle from low level to high level. And since the effective positive, that means the distance increases on an average by 146 units when I change the setting of release angle from 145 to 160. This is the technical meaning of this 146. Now I also do the effect of firing angle. Now average at high level of firing angle. Now these are the firing angle is high at the last for the last two runs. So it is easy to find the average of these two, which is 261.5. And average at low level is average of these two runs, 328 and 439, which is 383.5. And I just copy this formula. And the effect is minus 122. That means the distance reduces if I increase the firing angle, because the effect is negative. The last part is the calculation of interaction, which is now the symbols I use here, and a plus one symbol is here, which I am making red. Now, if I want to calculate the high level effect of interaction, I take the average of 328 and 352, and which is the which equals 340, and the low level average equals average of the other two, which is 305. So the effect of interaction, I can just make a copy of the formula. 340 minus 305, that is 35. I will explain this by graphs. Is there any question so far? This is a point where there may be a question.
Sir,
Sir,
can we make some decisions on the basis of this table? Say, for example, if we increase the angle by 1 unit, then the effect will be 146 divided by 15. Can we say that?
I will explain that because you can develop a regression equation also from this.
Okay, great.
I will explain the regression equation. Yeah,
Sir,
yeah. Any other questions?
high and low, does it mean the maximum and minimum in the setting?
I didn't get the question. Can you repeat, please?
Sir, high and low settings you have made. Is it the lowest possible ones and highest possible ones in
No,
the
no, these are
experiment?
not the lowest and highest possible. These are chosen by me for the experimentation purposes.
Okay. Okay, sir.
Now, the
Okay.
consideration for that, I will just explain it to you, friends. What is the consideration for that? Okay, I will explain on this only without the grid lines. See, what happens is you are going to develop what is known as effect plots. What are the effect plots? Let us say you have this. This is your factor setting, and you have low level setting and you have high level setting. Okay. And this is your response Y. So at low level, let us say you get this as response, average response, and at high level, you get this response. So your effect is like this. And the total effect that you are calculating is the difference between the two. So you are saying that the effect of my factor is this much. Now the question is, what does this dotted line mean? The dotted line actually means that I'm assuming that this response is going to change in a linear manner. Have I verified that? Not really. I am assuming that the response is changing in a linear manner. So this is called assumption of linearity. The question is now, if you put the levels at very large distance, let us say I'll just show you. Let us say you choose the level difference very large, and you are assuming that the variation is like this. But in reality, it is non-linear, and let us say it is actually like this. It is a non-linear response. You haven't verified this. Now, the interim value prediction, which somebody was asking how to predict it for the interim values, etc. Let us say I am predicting for an interim value here. My prediction, because I'm assuming linear, will be here. Y cap, you can say. But the actual y is here. So there is an error in my prediction, which is quite large. So the non-linearity can introduce errors, especially if the difference between these levels is very large. Now imagine that I reduce these levels to a much lower value. Let us say only from this much to this much. Now my response is nearly linear. I can assume linearity for it's like, let us say you got a circle, and a small portion of a circle can be assumed to be a straight line. But if you're talking about a large portion of, then it is a sector. So that's why the difference between the levels should not be too large, number one. Number two, if it is too small a difference, then you got other problem. Let us say you set the difference very small. Now your effect is, let us say you are having effect like this. The effect now that you are getting is so small that this small effect may not be accurately measured by your measurement system, and you may get a measurement error which interferes with your effect calculations. So very small difference between the levels can create measurement issues. Very large difference can create non-linearity problems. What is the solution? Okay, choose the level differences which are not very large or very small. The other choice that you have is, sometimes people choose a center point and you verify whether the center point response is generally lying on this line. I am not going into the details. There is a video separately done on that. So you can look at that video, but you can add a center point, and that added to the design, and you will need to use the software a little bit and find out whether the center point response is significantly different or not. So the difference between the levels is to be decided by these criteria. But these are not the minimum and maximum that you can set on the equipment, not necessarily. That may be a constraint in reality, and you'll have to consider what is it that you want to check and where is it that you are going to use the equipment. That is the main thing. Have I answered the question?
Yes, sir, very much. Thank you very much.
Okay. So now we have calculated the effects. Now let us plot this. I'm just going to open Microsoft Whiteboard, or even actually not required. I can use this sheet too also, or sheet. We can go further here, and I can say I can copy this. Paste people.
Yeah, sloga.
Yeah, please mute yourself.
Participant, please mute yourself.
Yeah. I think I will use the whiteboard. I'm going to use the whiteboard to explain this. That's more convenient. Just starting the whiteboard. Okay, I'm going to use the graph paper. Here, where is the graph paper? Do you see a graph paper? Maybe here. Anyway, it doesn't matter. Graph paper is not very critically important. Okay, I'll paste the that table here and show you how to plot the main effect and interaction plots. First, let us do the main effect plot. Okay, so let us first do the plot of release angle. So on the x-axis, I say release angle. What is the low value? Low value is, okay, I'll just put low and high, but we know what are the values. The low value of release angle was, yeah, I'll also copy this table best. So these are the low and high values. So the low value of release angle is 145. Yeah, and this was 160. So there is a difference of 15 units. The average at low level, as we know, is 249.5. So I'll just mark it as 249.5. And the high level average is?
ठ असते की माठ ठ असते ठ चिट्ट
Can you please mute yourself? I think all participants, may I request you? So this is 395.5 typically. And if I assume linear response, I join like this, and the effect of this is we have already calculated, and that is the effect equal to 146 units. And this is the main effect plot for release angle. Now I do another main effect plot for the firing angle. I'll just say FA firing angle, and the low value is firing angle 110 and 130. And at 110, the average is now, 110 average is 383.5. So here it is 383.5 somewhere here. Point 0.5, and average at 130 is at high level. So that is equal to 261.5. And that is somewhere here, As you know, this is a negative effect, and this value equals minus 122. That is the effect of firing angle. So this is easy. Now these are the main effect plots. The last part is the interaction plot, which I can plot in a similar way, but it is usually done in a different way. So I'll just say AB, and this is -1 and +1, high and low and high. You know the average at low level is equal to 305, and at high level it is 340. So 340. And this effect is 35 units. So the interaction is plus 35. But it is actually done in a slightly different way, which I will explain. and it is split into two parts. The experiment is actually divided into two parts for the interaction. So what we do is we first look at the, say I select this table and select a filter. Okay, I say filter. And now let us say I look at the experiment, only that part of the experiment when the release angle was 145. So I select only 145. Now remember, I am looking at only that part of the experiment when the release angle was 145. And now I'm looking at the effect of firing angle. We change from 130 to 110 to 130. So if I copy and paste this, I just use the interaction here. Okay, so this part now on the x-axis, I will put the firing angle. And now the low level and high level values. I'm going to put the low level value as, what is the low level value? Firing angle when it is low, it is 110, so 328. So I put 328. When the firing angle was low, and when the firing angle was increased to 130, it went down to 171. So I mark it as 171. Sorry. But this line represents only that part of the experiment when release angle was equal to 145. Only that part of the experiment. Now I select the other part of the experiment and plot the other line. So I change the release angle selection from 145 to 160. And now here I got the other result, which I will again paste here. It is here. I'll use the red color now, just for the purpose of differentiating. Now, this part of the experiment is done 160. Now, when the firing angle was low, what is the response? 439. So I use here 439. This is not to scale. 439. And it reduced to 352, which is again here above, it is above the other one. So it is somewhere here. But this represents the release angle equal to release angle 160. So there are two lines. Now, what is the difference between 439 and 160? This is the effect 439 minus, I can do it here, or minus 352. This is 7, this is 8. Yes, 87 units. So this is 87 effect when release angle was equal to 160. But now if I choose the other setting when the release angle was 145, the difference now is this much, and that is given by 328 and minus 328 minus 171, and this is equal to 7 and so 57, I think. No, 157. Yeah, the difference is 157. So when the release angle was 145, the effect of the same factor was 157 units. Whereas when the release angle was set at 160, the effect was 87. So there is a difference between the two, and the interaction given is given by half the difference between these two. So what is the difference between these two? 157 minus 87. So this is 70, and divided by 2 is 35, which is the effect that you got in your table, half the difference. I'll remove the filter. Yeah, you can see that this effect was 35, which was half the difference between the effects. Now, as far as this interaction effects are concerned, you can get different types of plots. If you get parallel lines, that means the effect is identical. This shows no interaction. No interaction. But you can also get like this. This is a strong interaction. You can also get the other way around. This is also strong. This is a positive interaction. This is a negative interaction when it is reducing, converging, diverging. You can also sometimes get a cross actually. You can also get a cross which is similar depending on where you are actually experimenting. So these are all strong interactions, but parallel lines show no interaction. So this is in general the interpretation of the main effects and interaction. Questions at this point? So we have done some part of the analysis. I'll explain a few more things about this, like the regression equation.
So, sir, since this is an example from engineering background, right? That and you have taken only two particular factors, that is release angle and firing angle.
Now you can add number of factors, but if you add third factor, the number of runs will be doubled because it is 2 to the power 3, that is 8 runs.
Yes, sir. Yes, sir. Definitely, you have discussed this thing in the initial part.
Yeah.
Now a small example, if I take from the management field, let's say there are two factors. One is debt to equity and another is liquidity. Okay.
Okay.
And how these two are impacting the profitability, which is why that is the.
But you will have to actually do that experiment. How will you do this experiment? You will have to do it in different regions.
Yes, we can do it using different regions or within the same company by creating the
How
sales
you can
values.
see the debt to equity ratios? It is a result of many things in the company. So really speaking, if you cannot set the levels, you will have to get down to regression kind of an idea. That means use the historical data and see what is the effect of changing different values of debt, equity, etc. So the regression is more commonly used in those kind of problems. Not that you cannot do experiment, but it depends. I cannot comment whether you will be able to change the debt to equity ratio in your company easily.
Okay.
I mean, is the management going to allow you to take different loans because just you want to experiment on different debt to equity ratios? I doubt. Or you can't change the equity because you'll have to release additional stocks or dilute or something. So this is a very difficult thing to do in real life. So I would say that since the changing the levels of the factors is very difficult in this case, you'll have to resort to probably historical data of different values of debt to equity ratios and factors and perform a regression or multiple regression. That's what I would comment on this.
Thank you, sir. Thank you for guiding me, sir. Thank you.
Yeah.
Excuse me, sir.
Yeah.
Will you please explain how you have come up with the value of 340 and 305 AB interaction?
340 and 305, no?
Yes, sir.
So here, have you seen this table which was created for with the coded values?
Yes, sir. I have created my own table also.
Okay, so AB interaction 1 minus 1 minus 1 plus 1 is there, right?
Yes, sir. Yes, sir.
On our high levels, and the average of the high level is 328 and 352. If
Yes,
I press the
sir.
control button, 328 and 352 control, you get an average of 340,
Okay. Thank
which
you,
is a
sir.
high level average. And the -1 is the low level. And the average of these two is control, pressing control button, you will see the average is 305. Got it?
Got it, sir. Got it. Thank you.
Now I'll explain the regression part. I will explain the regression part. So this is the table of effects. So to be honest with you, this high level is actually -1. Sorry, this, yeah. And also the levels I will copy. I think I need to copy the levels also. Yes. Maybe I'll copy this table rather than that coded levels only. Okay, coded levels. Now, if you are looking at the effect of any factor, let us say in coded values, let us say you are talking about the release angle, and -1 is the low value and +1 is the high value. Now, if I want to have a middle point or center point of this, what will be the value of the center point here, friends? It will be 0. Between -1 and 1 will be 0. I think I'll do that once again because the release angle needs to be a little below. So this is -1 and this is +1 and the center point is 0. Now the -1 average at -1 here, let us say we are talking about release angle. So I'm looking at this. So low value average is 249.5 and high average is 395.5. So what is the delta Y of this? This is I called delta Y, change in response. And delta Y I know is 146. That is the effect. What is the delta X corresponding to that? This I call it delta X, the change in the factor settings. How much is that? +1 minus -1. And that is equal to 2 coded units. So delta Y is 146 and delta X is 2 coded units. So the coefficient for release angle, if I make a regression equation, the coefficient is equal to delta Y upon delta X is equal to 146 upon 2 and that is equal to 73. How does this work? The regression equation that I'm creating is in this form: y is equal to a constant beta 0 plus another constant beta 1 into setting of the first factor x1 plus beta 2 into setting of the second factor x2 plus beta 1, 2, which is the regression coefficient for the interaction term into x1 into x2. All are in coded units. So I just add C to every X value. Now, as you can see, the coded unit difference is always going to be 2 because you are taking -1 and +1. For each factor, the delta X is going to be 2. So each coefficient is going to be half the effect. I hope this is clear. So the effect of coefficient of firing angle. So now let us say x1 I take as the release angle. So y is equal to beta 0 I will talk plus beta 1 I have found as 73. 73 into setting of x1 coded unit plus now what is the coefficient for firing angle? Half the effect of firing angle and that is equal to half the effect is -122 divided by 2 and that is equal to -61. So I'll say the second term becomes, this is -61 into x2 coded. And the last term is plus the coefficient for interaction term, which is equal to 35. Again, remember, that even for interaction, the difference in coded unit is +1 minus -1. So delta x is still 2. So the interaction coefficient is half the effect of interaction, which is 35 by 2, which is equal to 17.5 into x1 into x2. But these are to be in coded units. You can obviously convert this into uncoded unit, but I'm not going into that details today. There is a video on how to convert this into uncoded units, which you can watch. It is included in the list of videos. So this is the regression equation, and this regression equation gives me the predicted value of y cap, y cap. So for interim settings, you can add the coded interim values and get the predicted response for the interim values. So for any interim value, you can make a prediction of the response. Assumption, this is a linear equation. As you can see, each factor x1, x2, it is raised to the power 1 only. So that's why it is a linear equation. The remaining question is, what is this beta 0 constant? Beta 0 is nothing but average of all the runs, and which I can easily check. I just select all of them and find that the average is 322.5 below. So the beta 0 is 322.5. Average of all the runs. So this is my full regression equation of the predicted. This is how I developed the regression equation. Is this clear, friends?
Sir, can you please explain the last part once again, please?
Which part? What last part means beta
Sir,
0?
this beta 0 is equal to 322.5.
Yeah, it is just see, you have 4 runs: 328, 439, 171, 352. Just it is an average of all 4 runs.
Okay.
Which is 322.5. I'm just looking below, wherein the average I see is 322.5.
Okay.
The screen is little small, so you may not be able to see it very clearly.
No. I can see it.
Yeah.
Sir.
Okay, 322.5. Is it clear?
Yes, sir. And sir, one more thing.
Yeah.
When you were explaining the interaction effect, you told that the gap was change in y was 70, right? Between the two factors.
No, repeat, please.
No, in the interaction effect, when you were explaining, you showed there are two, you can say lines, parallel lines. One
Yes.
was the particular when release angle was 160 and when release angle was 145, right?
Yes, here.
So there was one particular was having a particular gap of or error of 87 and another was having an error of 157. Correct. So both again, if you take a difference, we are getting a difference of 70, right?
Yeah, whatever it is. Yeah, 70.
So 70 and
Half that is the interaction effect.
of that it is the interaction effect, that is 35.
Right.
So while doing the coefficient, why again we are dividing it by 2, sir?
So
Because
that's the coefficient that goes into the regression equation. This is effect. I'm not going into the details of why it is half. You can look at Montgomery's book and see the details of that part of the theory.
Okay.
There is a reference that I have given at the end of the training material, and design of experiment of Montgomery. If you look at it, it explains the details of this. Even the regression equation, uncoded, everything you can get there.
Okay, but it is of the same concept as you calculated, that is change in y divided by change in x, right?
Yes. But you can directly calculate also. You don't need to do like this. You're already done like this. Because
Yes.
you have done what is that high level average and lower level average. So you can easily calculate like this. Okay. So now,
Sir, what is the
yes,
what is
please.
the application of that correlation?
Application of?
What are the regression correlation we generated? What is the application of that? It may
It is
be in the next.
application for the prediction of interim responses. Now you have let us say you have a process and you want to predict some interim response, then you can use this regression equation. I will show in the next example. I do not know up to what time we can have this session because I have only 7 minutes left, but I have to cover one more example of this in Minitab. If we are going to close it at 9 o'clock only, then I will create this only in Minitab and show you. And another example, of course, you can look at the video. I can show this on Minitab. What is preferred? Because we have only 7 minutes left for this session. And I don't want to extend by more than 5-7 minutes this session. So shall I create this experiment on Minitab, friends?
Yes, sir.
Yeah.
Sure, sir. Please.
Or you want me to set the next one? Because this is a simple one.
Next
The-
one only you can demonstrate, sir.
The experiment that I wanted to show you is like this. The regression model I have explained here, which you can see in slide number 16, 17, 18. And then there are some terminologies, treatments I have explained. The orthogonality is basically equal number of sample sizes under treatments. So you can see that in your this thing, there are two, for each column, there are two rows with low and two rows with high levels, even including the interaction column. But none of them is repeating. So you can calculate independently all the effects and the sample sizes are equal. So such a design is called orthogonal design. Replication I have already explained. Yeah. A case study in full factorial design where three factors each at two level. The case study is like this. An engineer wants to evaluate effect of cutting speed, tool geometry, and cutting angle of on life of a tool in hours. He chooses two levels of each factor and performs three replicates. Data is available in the file called tool life DOE or tool life MTW. There is a response table that I have given. And the settings of cutting speed, coolant, and rake angle are given 40-50 cutting speed. Coolant levels are A and B, so it's not a it's a discrete factor. You can have either coolant A or coolant B. There is no interim value. And rake angle of the tool 3 degrees and 8 degrees. I am sure only the mechanical engineers would understand more details of this, but look at it from an experimental point of view. So what I will do is I will create this experiment in Minitab, and if time doesn't permit, we'll continue this tomorrow and then go to the fractional factorials.
So here, sir, the number of cases will be 8, right, sir?
Yeah, 2 to the power 3, but 3 replicates are there. So 8 into 3 will be 24 runs here. I will show you now on Minitab. I will create this. This is the Minitab interface. I'm using Minitab 17. You are using Minitab 21 if you have downloaded, or if you are using some other source Minitab. So I go to the top row is the menu command on Minitab, in which I use the stat command. Then DOE is the design of experiments, factorial, and create factorial design is where you create the design. Design matrix is created. So I click on create factorial designs. It offers you choices of two-level factorials, default generators, two-level factorial specify generator. Will not go to the other options. We'll select a two-level factorial design. The number of factors that we have in this case is 3. If you click on display available designs, it will show you different options. I will show this table again when we go to fractional factorials. But there are green designs, red designs, and yellow designs. And the green designs provide you the maximum information output from the designs. For the timing, let us remember that. And the red designs provide minimum information. They don't provide any information about the interactions. The yellow designs provide some information about interaction, but not partial information. And that is not for selection. In the designs, I have to select a design half fraction versus full factorial. Half fraction we'll see tomorrow. Right now, I'll select full factorial design. There is no center point in each replicate. The center points, as I said, are added to check the nonlinearity. I'm not adding center points. Number of replicates per corner points are 3. There are 3 replicates in the design. And the number of blocks, we will not treat different blocks. But let us say this was done on 3 different machines. Then we would select 3 blocks, and the 3 machine would be considered as 3 blocks. So I select full factorial, number of replicates 3, and blocks is 1. Now I have to define the factors and the settings. I have to look at what is the information. Cutting speed 40/50 is the first factor. So I type in cutting speed, low level is 40, and it is a numeric factor, high level is 50. Second one, if you remember, is coolant, and it is A and B, but it is not a numeric factor, so it is a text factor. So I say A and I say B, if I remember correctly. Yes. And the rake angle is 3 and 8. The last one is rake angle, and it is a numeric, and this is 3 and this is 8. I say okay. In options, you can select whether you want to randomize runs or store design. You want to store design and you want to randomize runs. So I just click OK. And I'll just say OK when the design is created for 3 replicates. So you can expect 24 runs on this. In the first column, you see the standard order. In the second column, you see the run order, which is randomized. Last will be one, and the full table of the design matrix. Now I can sort this table by standard order by clicking on Stat, DOE, Display Design, and select standard order of the design and just say OK. Now it will be listed in the standard order, and you can see that now the last factor, which is rake angle, if you look at the single replicate of this, I will just copy this in Excel for the sake of understanding. See here, this is the design matrix for a single replicate, Now here you can see that the cutting speed 40/50 40/50. So if you arrange this in coded values, it will be like this. This is low value, so -1 for the first 4 runs. And then +1. Then this is again split into 2 parts, -1, -1. I'm calling A as -1, and then 1, 1, -1, -1, 1, 1. And then this is -1, 1, -1, 1, -1, 1, and -1, 1. So this is the standard order created by Minitab. Of course, the run order is different. And now we have to fill in the response column. We are reaching 9 o'clock, and if we have to stop here, we will have to continue adding data on this design and spend about 20-25 minutes or half an hour tomorrow before the fractional factorial designs. Is that okay, friends? You will have to, those who have created these designs in Minitab, please save it by saying File, Save As, Save Project As. Don't save it as a worksheet, and save it somewhere that you can trace back immediately. And I will just save it somewhere. I will just say file name, DOE tool. Okay, DOE tool, not live, it is surface finish. Surface roughness. DOE surface roughness. And if I say, it will save the file. Now, when this matrix is created, I would like to clarify you that you are not supposed to type in anything here. You're not supposed to type in, because the matrix can get disturbed, and this is stored as a matrix in Minitab. So this is not only some numbers, but it is stored in the matrix form. So I would request the organizers to comment whether we can continue tomorrow on this, or you want to continue right now, and then because it's already 2 minutes past 9 o'clock. And there are 139 participants, so about 60 of them have already left.
Yes, I think, sir, we can continue on this.
We can continue.
Shall we ask the
Another 15 minutes?
participants? Are the participants okay with continuing? How much
Yes,
time we
sir.
would require?
We can continue for about 15 minutes from here. So I'll show the Minitab, complete Minitab procedure in about 15 minutes.
Yeah, no issue, sir.
No
Please go
issues,
No,
sir.
because if we continue tomorrow, then fractional factorial would get less time,
Yeah.
and that is something which is more complex, I think.
Well, yes, you are also right there. So the total time allocated itself is actually not sufficient for the
I know.
discussion. But that's why I sent all the video links also.
Urdhwareshe sir, I'm listening to you for the fourth time. Initially, 3 times I have listened to you offline, and today I'm listening to you online. But
Yeah.
every time, let me tell you, I'm getting something new out of it.
Oh, okay. Thank you so much. Interesting.
So, so I think if you could continue for 10 minutes, if you are okay with this, 10-15 minutes.
Yeah, 10-15 minutes it will take to do the Minitab. At least the basic level I can show in Minitab. Yes.
Yes, yes.
Okay. Thank you. So I'll again share the screen. So here I have to add the response column now. What is the response here? The surface roughness. Now there are 3 replicates, so there is a lot of data here. If I look at this, so this is your design matrix. The replicates are here and the data is given, but it will be too much for you to actually type in. So I have sent you a file called response tables. I suppose you have received the file. So if I open that file response tables, just give me a minute. I'll open the file response tables and copy the data. Are you having the file response tables, friends? Response
Yes,
table
sir.
DOE,
Yes, sir.
October 18. Great. So click on that file response table DOE October 18. And this experiment is actually, there are different worksheets. So the worksheet that you got to look at is DOE tool life. Not tool life. Is it tool life or are we talking about tool life, friends, or surface roughness?
Full life, sir.
It is tool life only. So that's correct. So I stored in a wrong way. It's not surface roughness. It's basically the life of the tool. Okay. So if I go to this, the sequence is exactly same. If you look at this -1 4 times and +1. So the standard order sequence is same. Rake angle, coolant and cutting speed. So if I copy the Minitab table here just for reference, it should match. It should match with this table because if I want to copy and paste this data, it should match actually. So you can see that 40, 50, 40, 50, 40, 50, 40, AABB 3333. So it's exactly matching. Now the surface roughness should be renamed as, no, I think I copied in minute, I pasted in Minitab only. I'm sorry. I should have pasted in this file, response tables file. Yeah, still it should match 33338888, 33338888. Then you got coolant 1122, 1122. Instead of we have said AABP, doesn't matter. And then 4050, 4050. Okay. So this is matching. Now I can copy the tool life column completely because it is in the same sequence. I just copy and paste it here. Of course, I will have to rename the column as tool life, not surface roughness. And I want to maximize the tool life. So this is where we are. Now I am ready to analyze this design in Minitab. If I go to stat, DOE, and factorial, now I go to analyze factorial design. Analyze factorial design. I click tool life here in the responses. I'll again show you if you are, since you are new to Minitab. In the response, the cursor will be flashing. So select the C8 tool life and either say select or double click on that. The terms that you have here in full factorial design are A cutting speed, B coolant, C rake angle. Now you got AB interaction, AC interaction, BC interaction, and also EBC interaction. So there are 7 effects. There are 7 effects that Minitab will evaluate. So I say, okay, I'm fine with that. I'll forgot to mention one thing. Include terms in the model up to order third means up to ABC, third order interaction. Now, I don't select any covariates. Graphs, I can select something. The Pareto is the default graph. Pareto means which effect is high and which effect is low. It will show on a relative scale. And then individual plots, I will just say 4 in 1. The discussion may take a little more, but I select 4 in 1. That is about the residuals. I'll talk about it and I'll say okay now. And I will see multiple things now. And if I want to see the basic regression equation and effects, then I say I go to session window and I see that here in the session window, you click on the window and select the session. In Minitab 21, it is slightly different. You'll have to look at that instruction. But now here you are seeing the effects of cutting speed, etc. I'll use a pen here now. Okay, so this is the table that you get, and you can see that the effect values, okay, the effect values and coefficients you see. So first you look at this, these are the effects of each of the factors. So what is the effect of cutting speed? It is 0.33 plus, that means the cutting speed improves the tool life by 0.43, 0.33, I'm sorry. The coolant improves by 11. The increase in tool life by coolant is very high from A to B. So B is better than A. That's what probably we will see. The rake angle also improves by 6.8. And then there are interactions which are here. And all coefficient you will see are half the effects here. You can see that, let us say, for example, this is 11.33. So the effect is half of that. So all effects are half. And you will see also the regression equation here. And the regression equation in uncoded units, it shows you how to predict the tool life. Of course, you don't need to make any manual calculations because Minitab is going to give you everything else. And then you will see what is known as the analysis of variance table. I do not know whether this ANOVA is covered in the inferential statistics session. Kindly clarify to me whether it was.
Yeah, it is covered, sir.
Very good. So analysis of variance is covered. So in that case,
sir,
you will. Yes,
sir. Sorry to interrupt, sir. Sir, how can I assess, like you have mentioned, the response table? Is it shared, sir?
Sorry, say that again.
Mm,
Response table.
few minutes back, you have mentioned that you have, yes, sir. The table you have already shown a few minutes
Yeah,
back. Is it
I share.
shared,
If you
sir?
want that to be shared again, I'll just put it in the chat box. But you should have received
Yes,
a
sir,
mail
please,
actually
sir.
from.
Yeah, it is
Okay,
received, sir,
mail.
in the
Okay.
Yeah,
Okay,
you
okay.
check your mail, you should be able to see that. That's not a
Yes,
big.
sir. Yes, sir. Yes, sir. Yes, sir.
Okay, it's also downloadable from our website, but I have sent that. So the ANOVA table, you can see the whole model, linear model, and which effects are significant and not. So you can see the p values here. Wherever you see low p values, those effects are significant. So these are significant. I'm sorry. So wherever you see low p values, those effects are significant. But you can also look at the what is known as a Pareto chart. So I go to Pareto chart for window. I can go to effect Pareto of tool life. Effect Pareto of tool life. Now this shows you beautifully relative values of the effect. These are not the actual values. These are transform values. But you can see that B has got the highest effect. So B has got the highest and this is the effect. And wherever you see that the effect is crossing this red line, this line corresponds to your alpha risk of 0.05. I'm sure you have learned this in differential statistics, what is alpha risk and beta risk. So this is your alpha risk. And
Yes.
whichever effects are crossing the alpha risk line, those are significant. That means B is significant, AC is significant, and C is significant. The rest of the effects are technically at this point not significant. But A is very low, but its AC effect is significant. So I have to keep is A in the model. AB is low, but and ABC is also low, but I will have to check whether if I omit some of the effects, what is going to happen. Now I will use Minitab to reduce this model, and Minitab has got a nice feature. So I go back to I think before reducing the model, it may be worth looking at the main effect and interaction plots. So I go to stat, DOE, factorial and factorial plots, and tool life, all three, and model, only model terms, or you can, here all terms are in the model. So you can just say okay here, and you can see all the graphs. Now here, I will look at the main effect plots first. Window tool helps you to decide that. So you can see that coolant has got the highest effect. So this has got very high effect. Rake angle also is pretty high, but this is a very small effect of cutting speed. Individually, cutting speed is not affecting to that extent, very small effect. But now let us look at the interaction plots. So I go to window and interaction plots of tool life. Interestingly, now there are 3 interaction plots, and you can see very strong interaction between what? This is cutting speed versus cutting speed versus rake angle. And this you can see is a very strong reversal. So this red one corresponds to response of cutting speed when rake angle was 8 degrees. And the lower one, the blue one, corresponds to effect of cutting speed when the rake angle was 3 degrees. So if you keep the rake angle 3 degrees, the cutting speed improves the tool life. But if you make the rake angle 8 degrees, it actually reduces. So this exactly is the effect of interaction, which we will never know if we do a one factor design. So, and these interactions, the other 2 interactions are relatively mild, but we'll have to check the p-values in ANOVA tables to judge whether we want to keep it in the model or we don't want to keep it in the model. We will ask Minitab to reduce the model, and we will I'm going to stat, DOE, factorial, analyze factorial design. But now I will go to stepwise, and method is forward selection, or you can say backward selection. Backward means it will select first all the terms in the model, and whatever is not significant, it will keep on removing. Alpha to remove, I am just keeping 10% because it may be a good idea to keep a 10% alpha risk here. So that's it, and display the table of model selection details. Now Minitab will automatically omit those factors and interactions which are not significant at 10% alpha risk. I just say okay, and I will get a revised Pareto chart. Go to again effect plot of Pareto. Yes, this is a revised Pareto now. Now you can see that only 4 terms are left in the model. B, A, C. You can see here B, A, C, C, and A. A is not significant because it's not crossing the red line, but you have to keep A in the model because AC is an interaction which is significant. So I keep A in the model. Otherwise, the model becomes so-called non-hierarchical. So this is the Pareto chart. And now if I want to predict the results or optimize the results, I can use 2 tools in the DOE. I go to stat, DOE, factorial, and then contour plots and surface plots. I first use the contour plots, and responses tool life generate plots of all pairs of continuous variables. There are two continuous variables. Therefore, there will be only one plot because coolant is not a continuous variable. So there will be two panels, one for coolant A and one for coolant B. And I check this. So this is for coolant A. You could, of course, have another one on coolant B. So this one is for coolant A. I think there will be another one for coolant B. I think I should have chosen in separate panels on the same graph. Okay. Okay, coolant A is selected. There should be another one which is for coolant B. Control plot of versus. Okay, this is the one. Why the other one is not selected? I don't know. This is for coolant A. Maybe, yeah. You have to select a setting here in the settings. And here it is coolant A. And now if you select a coolant B, you will get another one with coolant B. Yeah. And now here the beauty is that you get a contour plot, which is the response contour based on the two factors, cutting speed and rake angle. And the third factor is coolant B. As we know, coolant B gives you higher tool life. So let us look at this graph for coolant B. And I do a right click here. And I select a crosshair here. And I move my crosshair on this graph and see where I get the maximum tool life. You can see that the leftmost corner point gives me tool life of 53.9. You can see at the top what is the tool life on the top left corner of the graph or the graph panel, you can say. And if I move, you will see the change. And if I go to the blue zone, it is much lower tool life. Obviously, you can see color codings also. Here you are saying that you can get 52.5. So you can get the best settings out of it. The other choice that you have is actually there is a response optimizer that you can use. I will also show you looking at it, the same continuous variable, and I select coolant B. Sorry, you could select A and B, A or B, whatever you want. And you will see this as a 3D this thing which you can rotate and but this you can't use it for any analysis. This is only for looking at the variation with reference to cutting speed at rake angle. And you can see that this is the best point that you are seeing, and which happens at 40 cutting speed and rake angle of 8. That's what you are seeing. Now you could also use response optimizer. The last point today, before we close, I go to stat, DOE, and I go to response factorial, and then a response optimizer. And here, the response is tool life. Goal is maximize the tool life. Target, since you are saying maximize, you can go to the setup and say, okay, the lower value that you want is at least you want a 45 tool life. And target you are keeping 60. Obviously, it's going to maximize. There are other settings that you can use. I'm not going into that. Weight and so these depend on whether you want to give more importance to extreme values, etc. I'm not going into those details, but and it doesn't make usually major differences. So I click OK here now. I want to maximize the tool life. And in the options, I think, yeah, there are no constraint. In coolant, I select B only. Okay, anyway, it is going to select automatically, so I don't need to. And confidence intervals, type of confidence interval is two-sided. So I just go to this OK. And it is going to tell me what is the best choice that I have. Obviously, it's going to give you coolant B. It's going to give cutting speed 40 and 8, which we have seen uh, in the contour plot also. But there may be interim values which it might give. The predicted tool life that it has given is 54.166. And since you had given a target of 60 and the lower value was 40, it says that the achievement is D value gives me the desirability value. to what extent I have achieved the target, which shows 61% achievement towards the target, because it gave 54. It is between 40 and 60, and it has gone 61% towards the target. That's what it means. So this is what you can do in Minitab. I had to go a little fast on that, but the session is recorded, and I request you to look at this session again before coming back tomorrow. If you get time, I cannot say whether you are going to get time, but if you get time, half an hour, 45 minutes, you can have a look at this session again uh, before I declare the closure of today's session. Any quick question if you have? Of course, there are only still 112 participants, which is not bad. Half of them have.
So thank you so much. Actually, it's a wonderful presentation, sir. But a small query actually. Can you apply this? Can you apply this in management social science research, sir?
Yes, social sciences, the experiment often becomes quite difficult. It's not impossible, but it's difficult. For example, let us say in psychometrics or HR, people do these kind of experiment or marketing.
If you show me any small example, like, it will be helpful, sir, because we
maybe
understand the
I'll think of
concept.
it and talk about it tomorrow.
Hello,
Yes,
sir.
sir.
Hello, sir.
I'll give you the example
Hello.
tomorrow. Maybe. Yes.
Sir, what is value of alpha that we have to take for this?
Generally, alpha risk is taken at either 5% or 10%. That's a chance of missing the effect. I mean, the effect is there. The effect is actually not there, but you are considering that it is there. Not missing the effect, actually considering that the effect is significant, but in reality it is not. You have learned that in inferential statistics. So here you are assuming that none of the effects is significant unless the p-value is low. So whenever the p-value is lower than alpha risk, you will say that the effect is significant. But the risk that you are taking is the alpha risk, 10%. That means there is a 10% chance that there is really no effect, but you are considering that the effect is there.
Okay. Sir, which type of that is backward selection, forward selection, or stepwise selection? Which we have to
Both ways,
select?
it is going to give the same model. You have a choice. I generally prefer backward because you take the whole model and then it reduces the model and omits the terms which are not significant.
Okay.
It's very simple. You can do it manually also, but it takes a little more time.
Okay.
That feature is there in Minitab, so why not use that? And forward selection, you start with no factor, and then you go on adding one first factor, second factor, third factor, interaction, etc. That's the way the forward selection goes. You can try it forward selection for the same example and see whether you get the same model again.
Okay.
I will talk about the residuals tomorrow. I haven't talked about the residuals. That will require a little bit of explanation.
Okay, thank you, sir.
Save the Minitab file. We may spend 5-10 minutes on that tomorrow before we go to the fractionals.
Sir, can you please give one example from finance field as well, please?
I will talk about these possible examples tomorrow, not today, because already we have overshot by about 26 minutes. But the examples are not too many, because changing the situation in design of experiment, you are changing the levels of the factors. Somebody was mentioning about that debt equity ratio and other things which are difficult to change. But let us say in marketing or in finance, let us say you want to decide on some discounting policy. Let us say you offer a discount of 5%, 10%, 15%, etc., and see what is the effect on the sales. And there may be another factor, product A, product B, or something like that. So I divide the all India level or international level into multiple zones. Let us say 4 zones. If you are working in India, let us say I decide north, south, east, west, and I tried these policies in 4 different zones. The 4 different zones being blocking factors kind of thing, or they can be levels also. And you can try different policies in different regions and see what gives you the best choice. You are assuming that the behavior of the people in all regions is similar in that case. Just for example of that management example, to give you that.
Okay, sir, can it be possible? Say we will also think today, but can it be possible? Let's say as you told that different
Maybe
products are there.
tomorrow I'll think about a few more examples if they are possible. Yeah.
Let's
Sir,
say there are few products like equity, debt, and you can say fixed income. Choice between the products if it is changing.
It's very difficult to comment on this question before I know a little more information about the particular question. Maybe you can give it in the chat or write a mail, and maybe I'll be able to comment on that.
Yes, sir. Can you provide your email ID, please, sir?
Email ID is there on the
Yes,
material, page
I will
1.
provide it. I will provide it.
Yeah, but it's there on the material on page 1 also, slide 1.
sir, I want to lastly ask one question.
Yeah.
I didn't know much about Minitab. I want to learn from the scratch, from where I start and from what is the website.
You can watch my videos on Minitab. There are many videos that I have provided the links to 100 videos. Out of this, probably maybe 15-20 are on Minitab, and there are look at the DOE videos on Minitab, and you will get quite a few insights from that.
Okay. Okay. Thank you so much.
There will be
Highly
videos on
appreciate your.
Minitab also, but I don't know how good those videos are. But I generally get feedback that my videos people are able to implement that or use
Yes,
it.
sir. It is. Yeah. The session is very informative, sir. We are really enjoying this session. Thank you, sir. Thank you.
Okay, appreciate that feedback. Okay, then let us close the session.
Yes, sir.
Kalpesh, you
Yes,
want
sir.
to make some closing remarks?
Yes, yes, yes. Sir, on behalf of Department of ENTC, I would like to extend our sincere thanks to Hemant sir for delivering such a nice, informative and engaging session on design of experiment, full factorial design. Sir, today you